Write the full mechanism for the propagation steps in the reaction given below. Show all electrons involved in bond formation and movement of electrons with appropriate curved arrows. Use the provided bond dissociation energy table to calculate delta H for each propagation step and delta H propagation. So this is a classic exam question that asks us to write the full mechanism for propagation. Propagation 1 will involve the formation of the alkyl radical. In this case, we're using cyclohexane. Propagation 2 involves the formation of the alkyl halide. In order to start propagation 1, we need to assume that initiation has occurred. We know that free radical substitution is initiated by the homolytic bond cleavage of X2, in this case Br2. The Br2 bond breaks homolytically, which means one electron proceeds to one bromine and the other electron goes to the other. This differs from heterolytic bond cleavage because the bond essentially breaks directly in the middle. To show that, we use fishhook arrows. The result is two bromine radicals, which we can use in the propagation steps. So, assuming the abundance of bromine radical, we can begin with propagation 1. Now the products of propagation 1 are the alkyl radical and HBr. To form that, one of these hydrogens on any one of these carbons needs to undergo homolytic bond cleavage, which is catalyzed by the bromine radical which is formed in the initiation step. So arbitrarily, let's use this hydrogen right here. Now the carbon-hydrogen bond undergoes homolytic bond cleavage, where one electron returns to the carbon and the other joins with bromine to form HBr. The result is the alkyl radical at position 1 with only one hydrogen left behind and the formation of HBr. Now in propagation 2, we take our alkyl radical and react it with even more Br2. So here is my cyclohexane radical, and even more Br2 can undergo homolytic bond cleavage. The Br2 bond breaks, one electron traveling to each bromine, and the radical electron on the alkane joins with one of the electrons from the Br2 bond, which forms our alkyl halide, 1-bromocyclohexane. And that's the entire mechanism for propagation. We start with our starting material, which reacts with a bromine radical to form the alkyl radical. We then take that alkyl radical and react it with even more Br2, which undergoes homolytic bond cleavage and allows for the formation of the alkyl halide. So now we need to calculate delta H for propagation 1, propagation 2, sum those together to get delta H propagation, which is just the net result of propagation 1 and 2 enthalpies. To do that, we need to use the bond dissociation energy table. Throughout propagation 1 and 2, bonds have been broken homolytically and formed homolytically as well. In propagation 1, the carbon-hydrogen bond broke homolytically and the HBr bond was formed. Thermodynamically, bond formation is exothermic, so the enthalpy will be negative. Bond breaking, however, is endothermic, which has the associated positive sign. Delta H P1 is equal to the endothermic homolytic bond cleavage of the carbon-hydrogen bond, which is reflected right here, positive 422 kilojoules per mole. And the formation of the HBr bond is essentially the negative value of the homolytic bond cleavage or bond dissociation energy of the HBr bond. We said that bond formation in this case is exothermic, so we have a negative 368 as the bond formation value. Solving for delta H P1, we get positive 54 kilojoules per mole. Delta H P2. So now let's look at the second propagation step. The Br2 bond breaks homolytically, which means we have a positive 192 kilojoules per mole. The bond that forms is the carbon to bromine bond, which has an associated value of negative 301 kilojoules per mole. Solving for delta HP2, we get negative 109 kilojoules per mole. So just by these simple calculations, we can see that the formation of the alkyl radical in the context of monobromination is endothermic, but the formation of the alkyl halide is greatly exothermic. So the net result is that energy is released in this reaction.